Welcome to This Explainer. Today, we're acting as your guide through the highly systematic blueprints of Gemini Robotics 2. We're exploring a monumental shift in technology, how software is completely and fundamentally reshaping the physical world. If you want to understand exactly where the future of automation, labor, and hardware is heading, you are in the right place. Here is our roadmap for today. First up, a new paradigm. Then, detaching the brain from the body. Third, we'll tear down the Gemini architecture before jumping into physical realities and hurdles. And finally, we'll map out the strategic battlefield.
Let's kick things off with Section 1, a new paradigm, the android of robotics. Imagine a single centralized AI brain floating above drastically different machines, like a humanoid, an industrial arm, and the quadruped dog. That is a universal, common intelligence layer in action. You see, the goal isn't just to build one perfect robot anymore. It's to build a brain that can inhabit absolutely any of them. Think back to the early smartphone era. Remember when every single phone had its own clunky proprietary software? Well, the mobile operating system changed all that, totally liberating software from specific phone hardware. We are now seeing that exact same transformation in the robotics era. Gemini OS aims to be the universal operating system for the physical world. It acts as the centralized mind for any robotic chassis, whether that's an Apollo humanoid or a Dexmate arm. It completely shatters that old bottleneck where you had to train a new AI for every single specific robot.
Moving right along to Section 2, detaching brain from body.
In the old paradigm, each robot had its own isolated, specific control architecture boxed right inside of it. That meant incredibly high individual training costs, right? Because every time you built a new machine, you were basically starting from scratch. But shifting to this new era of physical AI, the defining metric of a robot is no longer just how fast its gears spin or how strong its motors are. Now, it's all about how smart and portable its software ecosystem is. The intelligence is a shared asset in the cloud, injecting knowledge down into varied joint structures instantly.
Okay, Section 3. Let's do a teardown of the Gemini architecture.
So here's the master blueprint for this decoupled architecture. The robotics stack is elegantly split into 3 distinct layers to optimize the computational load and achieve true hardware independence. Up top, you have the director, in the middle, the executor, and down at the base, the edge adapter. By separating the thinking from the doing, this system can adapt to literally any body. Let's actually break down what each of these layers is doing.
Zooming into that top layer, we have the ER2, or embodied reason layer, acting as the strategic director. Imagine a robot attempting to pick up a bunch of grapes to put them in a bag, but it applies way too much pressure and just crushes them. In the old days, the robot would just loop an error code and freeze up. But here, the ER2 actively converses with the robot's state, recalculates on the fly, and formulates a new tactical shift. It might decide to hold the bag open and drop the grapes indifferently to get the job done. It is reasoning in real time.
Dropping down a level to the VLA, or Vision Language Action Layer, we can track exactly how an abstract command becomes physical reality. Say the command is put the watering can in the bottom green box. First, Node 1 scans the room. Then, Node 2 coordinates the legs to navigate over to the table. Node 3 tells the torso to crouch, perfectly aligning the center of gravity. And finally, Node 4 executes the precise hand placement. The VLA is basically translating human language into full-body, continuous physical movement.
And finally, we hit the base layer, on-device 2. Because this executes directly at the edge, meaning right on the robot's own internal computer, it achieves zero latency. It doesn't have to wait for the cloud to tell it how to react to a sudden physical bump, and this is huge for scaling. Different chassis can adapt to new, complex tasks using under 200 examples, taking just a few hours. The cost structure of robotics flips entirely when you don't need months of data collection just to teach a new arm a basic task. But it's not all perfectly smooth sailing. That brings us to Section 4, physical realities and hurdles.
We call this the posture penalty. Look, for us humans, bending down to pick something off the floor is pretty trivial. But for a robot, as it bends, its center of gravity destabilizes, the complex kinematics of its knee joint strain, and its own body physically blocks its camera sensors. The data tells a pretty brutal story here. A shelf operation might have a 76.3% success rate, but once you force that robot to the floor, execution success drops to a dismal 45.7%. Gravity is incredibly unforgiving. Then there's the paradox of the light bulb dilemma. Removing a light bulb is a gross motor skill, just basic twisting and pulling, and robots hit a 92% success rate on that. But inserting it? That requires narrow thread alignment, matching angles perfectly, and millimeter-perfect blind rotation, all while missing tactile feedback. Because visual reasoning alone cannot feel those threads, the success rate for insertion plummets to 36%. It turns out what's incredibly easy for humans can be an absolute nightmare for an AI.
This forces us to ask some hard commercial questions. First, there's the hardware trade-off. Can this intelligence balance the exponential complexity of highly versatile five-finger hands, which suffer huge performance variance, against the less human-like but drastically more reliable two-prong grippers required in real-world commercial environments? And then we face the three ultimate hurdles for commercialization. Can these systems maintain unedited endurance in chaotic factories? Can they truly adapt with low data across different bodies? And ultimately, does the return on investment justify the massive capital expenditure of deploying them in the first place? Let's zoom out for Section 5, the strategic battlefield.
Right now, the market is fundamentally fractured into three distinct paths to dominance. First, you have Google's horizontal Android model, focusing purely on building a universal software brain to control third-party bodies. Then, you have the Tesla and Figure iOS model, a vertically integrated strategy demanding that hardware and software are built in unison for mass production. And finally, there's NVIDIA's infrastructure model. They are the underlying picks and shovels provider, essentially monopolizing the synthetic data and compute chips that everyone else desperately needs. Breaking down the economics reveals a direct clash of business models. Tesla's approach requires incredibly high capital expenditure because they have to manufacture and sell proprietary physical machines. Google, on the flip side, relies on scalable operating expenses. Their primary goal isn't selling metal. It's licensing a portable intelligence stack and expanding an entire hardware ecosystem via a universal operating system. It really is a battle of fundamentally different philosophies.
But the ultimate proving ground is this alliance flywheel. You have Google providing the top-down intelligence and NVIDIA providing the bottom-up compute engine. But the real strategic brilliance is the third pillar, the physical sandbox of Hyundai and Boston Dynamics. They're deploying this tech into raw, unedited, high-volume manufacturing floors. This isn't just some highly controlled lab demo. This factory environment serves as a massive closed-loop crucible, generating a data moat of physical reality that simply cannot be simulated or bought. Which brings us to the core thesis of this entire architectural shift. The ultimate winner will not be the company that manufactures the most impressive single robot, but the entity that builds the common intelligence layer powering all of them. As we wrap up this explainer, I want to leave you with this provocative reality to chew on. If physical labor is rapidly being converted into a highly adaptable, reusable software asset, who will truly control the future of our economy and the future of work when the brain no longer needs to be born with the body? Thanks for exploring these blueprints with us today. Keep asking questions, and as always, keep looking at the data.